Hello all, today we're going to be looking at comparison and limit tests. And before we just jump straight into it, I want us to actually think about what we're doing. So we are taking an infinite sum of numbers and we are adding them up. And sometimes that infinite sum is infinite, and sometimes that infinite sum of things is finite, which is actually kind of mind-blowing. So like here's a quick example of something that ends up being finite. And you can show that with the geometric series. But I want us to actually think about what we're doing. So we're going to be heading towards Taylor and Maclaurin series to help us approximate functions that we already know. And we've already seen ln of x. Well, actually today I think we're going to see what ln of x is going to be as a Taylor series. But all of these things have applications in physics, engineering, computer science, economics, modeling, approximations, and then also just helping us build our precision in problem solving. So I asked ChatGPT, what is the point of learning series and sequences? And this is a summary of knowledge. Okay, so like I said, we're going to be looking at comparison and limit comparison tests that we have today. By the way, all of these tests that we're doing are on our formula sheet, which I'm going to reference throughout this. And so if you're ever like, hey, what was that limit comparison? It is on the very, very last page, not on the back side, but on the front side of the very last page of our formula sheet. So hopefully that is helpful. When we are actually using comparison tests, we're using a series we already know either converges or diverges, and we're comparing that thing that we already know converges and diverges to what is in question. So for example, let's say that I am given this series right here. So the summation of 1 over n squared plus 1. And so we're like, hey, I don't know if that exactly converges, but hey, that's really, really similar to 1 over n squared, which that does converge because it is a p series and our p is greater than or equal to 2. So this one does converge, and the partial sums are all smaller than this thing that converges. And because we can compare these two things, we can say, hey, this also is going to converge. And this kind of works in the opposite direction too. So let's say that we're given a function like this, which we just have no idea how to kind of handle it. But once our n value gets really, really big, that negative 1/2 doesn't really make an impact. So we can compare this to a sequence that or a series that we already know diverges. And since this diverges and our series in question is larger than it, then this is also going to diverge as well. So that's everything what this comparison test is saying up here. So let's look for an example here, and I kind of want us to think about when stuff is on the bottom, when we have fractions on the bottom, it can be a little bit more tricky. So of course we can say, hey, I know that this is going to be larger than n cubed, but the second we flip them around, an interesting thing happens is I'm actually dividing by something bigger than over here, so my sign actually flips. Let's just do that really quick with numbers. So I know 3 is bigger than 2, but when I compare 1/3 to 1/2, I am cutting 1/3 into more pieces, so it is going to be smaller than 1/2. So we're kind of doing the same thing over here. And because of this because this is always going to be less than 1 over n to the third, and I already know that this converges because it is a p series where p is equal to 3, and that's bigger than 1. So I know that this actually converges here. I can say that this thing that is smaller than it also converges. Let's take a look at some more of these. And so it feels a little tricky. We're trying to compare this to something that we already know either converges or diverges. And something that is really, really helpful that I have come to find is by looking at kind of what the most simplified fraction or simplified function is. So almost ignoring like this -1 because it's not really going to matter as n gets larger and larger and we're adding it up. So really I would want to compare this to 1 over square root of n, which is really 1 over n to the 1/2 that I have right here. And that minus on the bottom is actually going to tell us that this is going to be larger than 1 over n to the 1/2. And I actually know some things about n to the 1/2. It is a p-series, and my 1/2 is less than 1, so I know that this is going to diverge. In fact, it's kind of like our harmonic series where we're still adding an infinite number of things, but it just doesn't get small enough fast enough in order for us to say that it converges. So this one is also going to diverge with p-series. And since this is larger than that, this is larger than that summation that we know diverges, this is also going to diverge. Okay, looking at our next one. So let's see, we do have an ln of n, and we also have an n to the 1/2 power right here that's kind of on our denominator. So if I'm also thinking about this, I could possibly compare it to, I know this is always going to be larger than that. So same kind of thing that happened up here where this diverges because of it being a p-series and it is smaller than this other function, this is also going to diverge. So our first two things diverge. This next one is kind of a little tricky. So I'm actually going to start over here, and I am going to look at that denominator in comparison to like which one actually gets bigger or larger. So I have something that's exponential and something that is like a root function. So exponential goes like this, root function goes like that. So this is going to get larger faster. So I want to just compare this to 2 to the n. And my 2 to the n's are kind of like the same on both sides, but I'm adding a little something, so that's going to be larger. Well, the second I actually flip these into my denominator, and I'm looking at comparing these, it's going to look a lot like that. Ooh, and now we can actually kind of see this as a geometric series, and since our ratio is less than 1, this is also going to converge, hence my value up here is going to converge because that 5 isn't really going to make or break it. Okay, this next one is actually kind of weird. So I'm going to compare my ln of n to, let's just say, n itself. So ln of n kind of looks like that, and n is just linear, so n is pretty much bigger than that. But if I flip these around, it is going to be larger. My 1 over ln of n, 1 over something smaller, is actually going to be larger because I'm cutting it into more pieces. So this is larger than our trusty harmonic series. The only ways that this falls apart is when n actually equals 1, because I would have 1 over 1, which would be equal to this. And so that is why we are starting at 2 here. Okay, last question I want you to try on your own, then pause the video and check your answer. So since these things are being multiplied, it is a little bit weird, but the n squared is getting bigger faster than the ln of n. In fact, the ln of n is almost kind of like we're multiplying by a constant, but our n is changing. So I'm going to compare this to n squared, and I know that that's larger. So now when I flip them over, I'll have 1 over n squared right here, which is going to be larger than my term, and I know that my series of 1 over n squared converges because my p-value is bigger than 1. So hence, this is also going to converge. So I'm just taking a step back, and there are 3 divergent and 2 convergent. When I first did this, my paper did not look anything like this. I had to play around with some functions, so feel free to mess up, and then instead of erasing your work, I just suggest crossing out your work because you can learn from it. You'll learn to not do it again that way. But yeah, a lot of times this just takes some playing around. Okay, next chunk that we're going to talk about. So right here on that last one, we were just comparing series to series. And now we're actually going to look at ratios of sequences over sequences. And see if we can use that ratio, whether that ratio is going to 0, whether it's going to infinity, to predict what one of those sequences is going to be. So I'm going to come back to everything that this says up here, but I want to actually just do an example first, and then we'll come back and we'll refer. So what I'm going to do is I'm going to pick kind of the most simplified version of this, which would have been 1 over square root of n. And I would like to be able to compare this, but with this plus 1, it's not always true. And so I have to think of a different way of actually doing this. I can't just directly compare these. What I'm going to do is I'm going to use this function right here that I have, that I know when I take the summation of that, that is going to diverge because my p-value is 1/2 and that is less than 1. So I'm going to take something that I know diverges, and I'm going to throw that in as my denominator in this. So this is my known value, and this is what I'm questioning. So my question's on top, my known value that I know diverges is on the bottom, and I'm going to look at the ratio between these things. So I'm going to look as n gets really, really big of these two things. I know it looks kind of confusing, but we can actually simplify some stuff out. So I am going to get rid of this fraction on the denominator by multiplying by n. And I'll end up with square root of n over square root of n plus 1. If you think of L'Hopital's, or if you even think about the rates of change of these things as n gets really, really big, they're going to have the same rate of change because that plus 1 isn't going to really impact it. But if you're wanting to show that algebraically, so I know this is going to eventually go to 1, but if you want to show this algebraically, I'm actually just going to multiply by 1 over square root of n, and you may ask, why the heck am I doing that? That is actually to get my n kind of back to the denominator, so I'll have a 1 up here. Over here, because I'm multiplying square root of n by 1 over square root of n, I'll just get a 1. And then when I multiply this, I'll have a 1 over square root of n. And so now you can kind of see as n approaches infinity, I'm going to have 1 over something really big. That's going to become 0, and I'll actually just get 1 over 1. So what does this actually show me? I put a function on the bottom that is, I know, divergent, which means it's going to go to infinity. And if the top part was convergent, I would have a number over infinity, and it would equal 0. But I have something that doesn't equal 0. I have something that doesn't equal 0, so I know that my top function can't actually converge. I have just shown, using I up here, if I have a limit and I know that my bottom part diverges, and I look at my limit, the limit doesn't equal 0, then I know that they're both going to be divergent. So I just showed that our thing in question, our series up here, is divergent. Okay, I'm going to try to actually do that with this one as well. And a really common way of doing this is we just have our function that we're trying to test, so question mark, on the top, and then we use a function that is similar to it, but maybe hopefully we'll be able to cancel some things out that we either know converges or we know diverges. So my in-person class wanted to use n over n cubed, and this actually might work, but it's a little bit harder to show. So because like stuff doesn't cancel out quite as nicely on the top and the bottom. So instead, I'm actually going to add this plus 1 in here, and you may say, hey, we actually still don't know if this converges or diverges, so I want to actually show that just real quick over here. I'm going to do n over n to the third plus 1 over n to the third. And again, I'm trying to show that these series are convergent. Well, this one right here ends up being 1 over n squared. Hey, that's a p-series, convergent. This one is already a p-series, which is a p equals 3. It's already convergent. So I have convergent, convergent added together. This is for sure convergent. And now I'm going to look at my limit as n approaches infinity, and I'm going to do a little algebra, maybe multiply by that reciprocal on the denominator. And so we can see that denominator cancels out, and actually this n plus 1 over n plus 1 ends up canceling out. And so I'm taking my limit, I'm finding my limit as n approaches infinity of n to the third over n to the third plus 1. That plus 1, not really going to make or break the deal. But my n to the third and my n to the third are both to the same degree, and so I'll end up approaching the same thing on top and bottom, which means that I will end up approaching 1 right here. And I could do that same trick where I multiply by 1 over n to the third on the top and the bottom, but I'll still get that same answer of my limit will be approaching 1. Well, what does that actually tell us one more time again up here? And I want to look at it. So we took something that converges. We took something that converges, so it's definitely not going to be this one. We took something that converges, and our limit did not actually equal 0. That's okay. But up here, if our limit did not equal 0, which is what happened and I just equaled some number, then they both are going to converge. And I already knew that my bottom function converged, so now I know that this top function also converges. My top series also converges. Okay, so for your practice, which remember this will be written homework that you're turning in, your hint, there are actually 2 convergent and 2 divergent right here on this page. My other hint on this is, especially on number 2 right here, when we're writing, like let's just say I was writing 5 factorial, that would be 5 times 4 times 3 times 2 times 1. And if I treat my 5 like my n, then down here on the bottom, I would have like 5 plus 1 factorial, which would end up being 6 factorial. I'm multiplying all the values that are 6 and below. So my hint here is maybe some things will actually cancel out, and you can see that they do, and I'm just left with that 6. Now, that was when I had my n equals 5. If I keep my n as just an n, that same kind of pattern will start to happen. So I could do this as like n times n minus 1, 1 less than my number that I started with, which over here I started with 5. 4 is 1 less than 5, times n minus 2. That would be like my 3 over here. 3 was 2 less than 5. I'm looking at 3 less than n, and then so on, and it would be like 3, 2, 1 at the end, all over, and then think about what you could write on the denominator. Okay, my hint for those next few is that you should scratch this out. So that's my biggest hint. Do not waste your time on this. It is something insane that you will not be learning for a few semesters in calc. It's like Deschert's test using Euler's formula. You do not have to do number 5, so just cross it out. Don't worry about it. My hint for 6 and 7 is one of them is divergent and one of them is convergent. And then last but not least, my hint for these two, if you try to write 8 as if it was a p-series, so you can kind of combine whatever is inside and raise it to the nth power. This number 9 is going to be extra credit, and make sure that you're showing all of your work on that. Okay, y'all, have a lovely day. Bye.